Hello students, in this video we will be studying about the planetary motion. So we have studied in the earlier videos about the energy diagrams in which we have studied the total energy, potential energy and kinetic energy. So we are going to apply those energy diagrams to our problem on planetary motion. We know that for a gravitational force, the equation is f of r is equal to minus g m1 m2 by r square, which is always attractive since negative term. Okay, now, so what is the potential energy, true potential associated with that? It is given by the equation u infinity minus u of r is equal to minus integral r to infinity f of r dr. So this is equal to, on substituting f of r, you get the relation as g m1 m2 by r. So u infinity to r, this is the amount of energy needed for a particle to bring a particle from infinite distance to a point r. Okay, so that we take u infinity as 0. So u of r, the potential energy, gravitation potential energy at the position r is defined by the relation minus g m1 m2 by r. Okay, now we know the effective potential energy has another term which is the centrifugal term, which is equal to L square by 2 mu r square minus g m1 m2 by r. So this is the effective potential, this is the centrifugal potential and this is the true potential. So in this equation, if L is not equal to 0, that means, and at smaller distances when r is very small, r square will be much smaller and this term will dominate. So a repulsive centrifugal potential dominates at small r. Okay, but at larger r, this term dominates. Okay, so this is the repulsive term, since this has a positive sign and this is a negative sign because it is an attractive potential term. Now we are going to draw the energy diagrams. So this is our energy diagram. The axis is R versus energy. You can see this is the effective potential energy curve. These dotted lines represents centrifugal term, which is the positive value, and this is the gravitation potential term. We have considered 4 cases. Okay, E greater than 0, E equal to 0, E less than 0 and E is equal to E minimum. From this, one more point is that there will be a kinetic energy which will be defined by the relation K is equal to E minus U effective. So our motion is always restricted to the region when K is always greater than or equal to 0. K can never be negative. Okay, so what are the different possibilities for these 4 values? In the first case, this is energy. First case when E greater than or equal to 0. So we take the graph of U effective and this is the graph of E greater than 0. So the difference between these two graphs gives their kinetic energy. Okay, when E is greater than 0, R is unbounded for large values. So the particles are always kept apart by the centrifugal barrier. There is a positive energy value for most of the cases. So the particles remain apart. Okay, they cannot come beyond a limit. Okay, that is called the centrifugal barrier. Now, so in that case, the particles are unbounded. Right. Now, second case is when E is equal to 0. So this is a barrier between it is a boundary between unbounded and bounded motions. Okay, which is the case when E is equal to 0. And the third case is E less than 0. E less than 0 is this case. So the motion is bounded for larger and smaller. So it is acting in between these 2 points. So it is actually bounded for larger as well as smaller values of R. So the 2 particle forms a bound system in this case when energy is less than 0. Now the fourth point is E is equal to E minimum at this point. So here R cannot be any other value. It is restricted to a single value. Therefore the particles stay a constant difference from one another. Okay, these are the 4 cases. Now we know that when energy is positive, E greater than 0, the motion will be hyperbola, and the second case when E is equal to 0, we get a parabola, and for the third case when E is less than 0, it will be the motion is in the form of an ellipse, and in case 4 you get it a circle. So there is one more possibility is that when L is equal to 0. In all these four cases, L was not equal to 0, and the first one was unbounded, the second one was a boundary between the two. Here is a bound system, here it is a minimum value. Okay, so if L is equal to 0, there is no centrifugal barrier, so the two particles comes towards each other along a straight line on a collision. That will be another possibility. Okay. Now we are moving into our planetary motion alone. We are considering a planet of mass m moving about a star of mass capital M under a gravitational interaction. So U of r is equal to minus g m by r. We take it as minus c by r. C is a constant. It is g m. Okay. Now we are mostly interested in the case of a particle, not a particle, a satellite orbiting around our planet. So these results are also applicable to those systems as well as to binary star system with two stars of masses m and m. Okay. Now if we consider a satellite of mass m orbiting around Earth of mass me, and then our equation for C will be in the equation here. You can have M, capital M becomes ME, and this is small m mass of the satellite, and small r becomes the radius of Earth, RE. So we substitute it as C is equal to GM_ME, that is equal to mg_RE square. So G is the acceleration due to gravity, which is defined by GME by RE square. Okay. Now we have the formal solution for an orbit, which I have discussed in the earlier video. That was theta minus theta 0 is equal to L into integral r0 to r dr by r square into root of 2 mu E minus U effective. Here we are going to substitute this U effective term. U effective, we know that it is the centrifugal term plus the true potential. Here it is minus C by R. Okay, so we substitute that in this equation and you get the relation as theta minus theta 0 is equal to L into integral dr by r square root of 2 mu. Substituting this relation and dividing throughout by 2 mr square, you get it as 2 mu E r square plus 2 mu C r minus L square. Okay, on integrating this integration is given in the note 10.1. You can refer the textbook for that. The result is nothing. R is equal to L square by mu C by 1 minus root of 1 plus 2EL square by mu C square sin theta minus theta 0. This is the solution, or after integration you get the result like this. The integration is given in the section 10.1. So in that equation you put some parameters. This is our usual convention. We put theta 0 is equal to minus pi by 2, and r0 we put it as L square by mu C, and that term in the square root you take it as epsilon. Okay, here this r0 is the radius of the circular orbit corresponding to the given value of L, mu and C. So r0 corresponds to the radius of the circular orbit. Okay, and epsilon is a dimensionless parameter which is called the eccentricity, which you might have studied in your maths classes, which characterizes the shape of the orbit. Okay, the value of epsilon as well as the value of energy, total energy, gives the shape of the orbit which the particle or the satellite will make. Okay, so we are going to substitute these two values in our equation. So here it will be r0, and this term is eccentricity epsilon, and theta 0 substituted as minus pi by 2, and you get it as cos theta. So our equation, the result r is equal to r0 by 1 minus epsilon cos theta. So in this equation you convert it into the polar coordinates r and theta. Okay, so what is r? R is a root of x square plus y square, and r cos theta is equal to x. So in this equation we cross multiply this equation, you get it as r minus epsilon r cos theta is equal to r0. Substitute for r is equal to root of x square minus x square plus y square minus epsilon r cos theta is substituted as x. So our equation, this equation becomes this form, and we square both terms and expand to get it as 1 minus epsilon square x square minus 2r0 epsilon x plus y square is equal to r0 square. This quadratic form describes the conic sections, which are hyperbola, parabola, ellipse and circle. So in the first case, when epsilon is greater than 1, hence E energy greater than 0. The system, we have shown that the system is unbounded system, and the equation reduces to the equation of a hyperbola. That means the shape of orbit when epsilon is equal, epsilon greater than 0 or epsilon, E greater than 0 and epsilon greater than 1, that particle will follow a hyperbolic path. Okay, this is the first case. The second case is when E is equal to 0. That means epsilon is equal to 1 in that equation. So our equation reduces to the equation of a parabola. So the particle, the nature of the motion will be in the shape of a parabola. And the third case is when eccentricity is between 0 to 1 and energy is between these two values. Then the system is a bounded system, and you get the equation in the form of an ellipse, elliptical path. So the satellite forms a or follows a elliptical path, right? Now the fourth case is when epsilon is equal to 0. Here E has its lowest possible value, which is equal to minus mu c square by 2l square. In that case, the equation reduces to the equation of a circle, where r is a constant. So in that case, when epsilon is equal to 0, the path will be in the form of a circle. These are the four conditions or the four different possibilities when the value of energy is varying in the case of any type of planetary motion, either it is a movement of a comet or planets or satellites or any bound system, etc. Thank you.